properties of logarithms. So we've had properties of exponents. We have quite a few of them. We have quotient properties and product properties and some power properties. Well, because exponentials and logarithmic functions are inverses of one another, then logarithmic functions also have their own unique properties. But as you look at them here, they're very similar to the exponential properties. For example, on the product property of a logarithm, you'll know that a product property in an exponential was when I had same bases multiplying together with different powers, and I was able to add the powers together. Well, look what we're doing here. When we have same bases of logarithms, I have a product of some value here. I'm able to separate that into addition between the two log values. And the quotient property, well, when we had that for exponents, we were subtracting the powers. Well, now we're subtracting the log values. And then a power property, this one's kind of unique. But a power property says the log of some number raised to a power of n. That power of n actually pops out in front and becomes this coefficient in front of our log. We're thinking graphically that that thing is doing, what that thing is doing is it's vertically stretching my value. So those are our three properties that we're going to work with today for this section. All right, let's say we were given the values of log base 3 of 12, approximately 2.262, and the log base 3 of 2, approximately 0.631. And we're going to use just those two logarithms. Both of them are the same base of 3. We're going to use 12 and 2 to somehow rewrite into the problems we see here for A and B. So I want to figure out how can I use 12 and 2 to come up with what we're taking the logs of for these next 4 examples. Well, 12 and 2, we can easily see here that 12 and 2 helps me get a 6 when I am dividing. So another way of writing log base 3 of 6 is to look at it as a quotient between 12 and 2. And if it's a quotient, what that really means is you're taking the log base 3 of 12 and you're subtracting the log base 3 of 2. And this is how we're going to come up with our approximate values for these things. Log base 3 of 12, 2.262 minus 0.631. We get that the log base 3 of 6 is approximately 1.631. And if I were to check this on my calculator, we're going to learn in a little bit how we can change our base from a base 3 log to a base 10 so that I can use this on my calculator. Some calculators actually have a change base option on them, but we'll come back and peek at that. But that's what log base 3 of 6 would be equal to, 1.631. If I'm kind of getting a ballpark figure, here's a way of mentally checking. I know that a log base 3 of 6 is the same thing as 3 to some power is equal to 6. Well, 3 to the first power is 3, 3 to the second power is 9, and 6 is in between those. So I'm somewhere between a 1 and a 2. And yeah, we're somewhere in between a 1 and a 2 there with 1.631. So there's a mental check that I can do for these things. How about a 24? How do we get a 24 out of a 12 and a 2? Well, again, that one looks pretty simple. This is a product now. And now that it's a product, it becomes the addition of two logs. And now we have 2.262 plus 0.631. Now we get an approximate answer of 2.893. Is what log base 3 to the 24 is. Again, 3 to what power? 3 squared is a 9, 3 to the third is a 27, and 24 is closer to 27, so that means I'm going to be closer to that 3 value, and 2.83 is closer. I'm using that approximation symbol because these are not exact, rounding those decimals. Log base 3 of 32. All right, now we're getting into something that maybe is not quite so obvious. 12 and a 2. Now, I don't have to use both of these to come up with these values in case of 32. I'm not going to be using the log base 3 of 12 at all. Think about what I can do with 12 and 2 to come up with a 32. Well, I can't multiply them together. I can't divide them. That doesn't help me. But I could recognize that 2 is a base 2 power number. So I could see that this is log base 3 of 2 to the 5th. That's 32. And now I've got a power property here, which means this is 5 log base 3 of 2. So I have log base 3 of 2. I know that that is 0.631. And then I get my answer here. So we can see properties at work. Okay. 3.155. And again, approximate for the solution. All right, but we'd like to actually be able to find a more exact value with that. Once again, coming up in just a little bit when we talk about Changebase. So, process of using our properties of logarithms sometimes require us to take one logarithm and blow it up, so to speak, into multiple logarithms. And then other times we're taking multiple logarithms and we're bringing them together as a single one. So expanding, making one log become multiple logs. Condensing, making multiple logs become one. So in this case, for A, that is a product going on right there, which means I can write this as log base 2 of 8 plus a log base 2 of x. And now I've expanded this. We're not solving anything. We're just rewriting the way that it looks, changing the way that it looks. What about this next one here? I've got a little bit of everything going on with this next one here. So I see product because of 3 times x squared. I see quotient, numerator divided by denominator. I see power. So what we're going to do first is we're going to just separate the quotient piece of it. So I have a log of 3x squared minus a log of a 5y cubed. Right? These are both base 7s. So there's using the quotient. And now I can use the product to separate the power pieces of those log values from the coefficient or integer pieces. So, for example, log base 7 of 3x as a product of log base 3, log base 7 of 3, times a x squared, so it becomes log base 7, 3 plus log base 7 of an x squared. And this one does the same thing. So a log base 7 of 5 plus a log base 7 of y cubed. Now, when I am subtracting and I separate one logarithm into multiple parts, I want to make sure I put parentheses around that because I'm going to have to distribute that negative. All right, then I have some powers. Power, so I'm going to have power properties at play here. So we've got now log base 7 of 3 plus, that power comes out, and now I get a log base 7 of x. And then distributing the negative, I get negative log base 7 of 5 minus, and then another power, so the 3 comes out front, log base 7 of y. And at that point, I've separated everything as far as I can go. So this is the expanded form for B. C, we have a product and we have a power. So first we deal with the power. we'll do with the product. We'll deal with the products always last. So log base 10 of 5, log base 10 of x cubed. Move that 3 power out in front, and I get my equivalent expanded form. So that's exploding a single logarithm into multiple parts. Other times, we're condensing them or want to rewrite them into a single log. And this is what we use primarily when we're solving a logarithm, which is our next section. So now we want to bring it all together. And we go left to right on the problem. And the first thing that we will do is we'll look for those situations where there is a coefficient out in front of our log or our natural log, because that coefficient becomes a power. And by the way, these properties work for both natural logs and logs, because remember a natural log is just a log base e. All right, so the first thing I see here is I see this 2. It's camping out in front of this natural log of 5, and it's going to go back and become a power. So we'll go step by step here. Natural log of 5 squared minus natural log of 10. Go ahead and simplify the 5 squared. So now I have natural log of 25. Then I'm looking here at the first 2, which is addition, so that becomes product. That's a natural log of an 8 times a 25, which is 200, minus the natural log of 10. So we're just multiplying these 2 together, which produce that. And then I've got quotient. So natural log of 200 over 10, finally giving me the natural log of 20. So be careful with the quotient property. It's not 2 natural logs that are dividing by each other. It's just a single natural log of a quotient. Let's try this next one here. Power, move it back. And then simplify our power, log base 10 of 27, log of 9, and I have a log now of 2 times 27, becomes a log of 54, and then I've got a log of 54 divided by 9, which becomes a log of 6. Expanding, condensing. Finally, the change of base. This allows us to use our calculator. Again, most of our calculators are base 10 only. Some of them have that cool feature that allows you to do other than base 10s. This will allow us to change something that's not base 10 into base 10. Now, in the formula here, see the formula log base c of a equals log base b of a over log base b of c. What we're going to do, since we want to work with our calculators primarily, we're going to just make that b, the base of these things, become log base 10. So we're going to make them into common logs. You can make them into any base you want, but for our purposes, for the use of the calculator, we're going to go ahead and make them become log base 10s. All right, so how do I remember when I've been given some log form of a base other than a 10? How do I know when I'm setting up change of base that I've got a numerator log and I have a denominator log? How do I know which piece goes where? Well, I remember it by, pretty simple, the base value becomes the base log. Like think of a house. You have a basement of a house, it's underneath. And so the base value is always going to be below. And another way of looking at it, log base c of a is written slightly above the c, so A is going to be on top, C is going to be in the denominator. And that's how we're going to change our bases to base 10s. So now, unlike a quotient problem where I have a log of a quotient, now this is actually physically a log divided by a log. All right, so let's check it out, see how this works here. So log base 6 24 The 6 is my basement, so it's on the bottom. And on the top, I have my log of 24. And this is what I'm going to do. I stick this thing in my calculator. My recommendation is to probably do it in pieces. So I would first of all find the log of 24. If I did that, I have 1.38. And then I'd find the log of 6. And I get 0.79 or 0.772. And dividing these two, oh, 0.778, sorry. Dividing these two, I get 1.77. You could also do it all at once, but you have to be careful when you do it all at once. So most calculators, when you put it in log, it puts a parenthesis up. And if I'm going to do the division of another log, I have to go 24, and then I need to close that parenthesis before I hit the division button. And then hit the log button one more time, and it's going to put up a parenthesis, and then put in the 6. And then you would hit enter, and you're going to come up with your 1.77. So if you did it that way, that's going to be a more exact number because we're not having to round anything. So just a little difference here. I get 1.773 instead of 1.778. So a little difference. But there it is. There's the Changebase in action, just simply recognizing which one is the numerator log and which one is the denominator log. So here in this one, log base 5. 5 to what power gives me an 11? Well, it's going to be somewhere between 1 and 2. So we go log 11, divide that by log of 5, get 1.49 approximately. All right, and that property will come in, this change of basis formula will come into play when we start to solve logarithms. So let's look at some application for our logs and some of our log properties. So in the Richter scale, which we know it measures the magnitudes of an earthquake, we've got the following function. We have the Richter scale number R is a function of the intensity of the earthquake, and that is equal to the log of a quotient. So we've got a quotient property going on right there. Well, those Richter scale numbers, an 8.0 quake versus an 8.2 quake, tells you how much larger the intensity of the quake was. So we're going to find out really on the Richter scale for this particular problem, what if one quake was 50 times larger than another one? So 50 times, we're talking about intensity here. All right, so how do I use this equation? Well, if we don't know what the actual intensity values were, but we just know a ratio of intensities, 50 times, that means our initial value, I sub O, we can just make it 1. We can make it 2 if we wanted to, but 1, and then I would be 50 times that. So we'd have log of 50 over 1, which really is just the log of 50. Now, this is a common logarithm, so I'm actually able to put this into the calculator and take the log of 50, and I discover basically 1.7. So a Richter number is usually to the 10th. So this is approximately 1.7. So the difference, if I had a quake that was a 6.0, a quake of 7.7 would have been 50 times as intense as that. All right, so there's some application for it. We also have application in pH. The pH, measuring the hydrogen concentration of a patient's blood, can be calculated using the Henderson-Hasselbalch formula. pH is equal to 6.1, which is constant, plus the log of the quotient B over C. B is the concentration of bicarbonate, C is the concentration of carbonic acid. And the normal pH of blood is approximately 7.4. So as our pH values get smaller, we have more acidic blood. If our pH values get larger, it's more alkaline. I believe that's right. So let's expand the right side of the formula for the first thing. So we're going to say that our pH level is equal to 6.1 plus the log of, now if I'm expanding a quotient, I'm going to be doing subtraction. So there's the expansion from the original formula. All right, now we're going to determine what our pH is given some values. Let's bring this up. So a bicarbonate concentration of 38, a carbonic acid concentration of 2. So 38 is our bicarbonate, 2 is our carbonic acid. So now we get pH is equal to 6.1 plus the log of 38 minus the log of 2. Well, log of 38 is 1.58. Log of 2 is 0.30. And I'm going to add that difference here. So 6.1 plus 1.58 minus 0.3 gives me a pH of 7.38, which is pretty much right on there for our normal blood pH level. And so to answer the next question, are we above or below? Well, we're slightly below. Makes it a little more acidic. And so, not by much, but each little change in the pH value is something. So we are a little bit below our normal value of 7. So there's an application using some of our properties of logarithms. There we go.